Alright, welcome back. So in this tutorial we are going to be looking at how to define the winding for a switch reluctance machine using QuickMachine. So the first step here, I'm going to just load in a very simple model, and with this tutorial I'm assuming you know how to fill in this whole page here to get a model on the right. And what we're going to be dealing with in this tutorial is all about this table right here, how you set up these phases and your windings for your model. So by far the easiest way to create the windings is by using this auto set button. So if I just hit this auto set button, you see a couple of things happen. First, you get two phases, phase A and a phase B. And you also get all of these numbers here, which we'll talk about later. But also you also get these numbers and letters for each winding area. Now the number represents the number of turns, the letter represents the phase. So this is phase B, this is phase A. Now to really understand what this auto set button does, I'm going to go ahead and clear all these phases out. We're going to start from scratch, and we're going to basically run the algorithm by hand. So the first step of the algorithm is to figure out how many phases you actually need. And the auto set button here uses the following formula. It first finds the greatest common divisor between the number of stator teeth and the number of rotor lobes. So in this case you have 12 stator teeth and 6 rotor lobes. So the greatest common divisor of 12 and 6 is 6. Now it then takes the number of stator teeth and divides it by that greatest common divisor. So we have 12 divided by 6 equals 2. So we're going to need 2 phases. So essentially what that formula is doing is you're breaking the teeth up into sets, where within each set each tooth is symmetric with all the other teeth in that set with respect to the rotor. So for instance, this tooth would be in the same set as this tooth, and this tooth, this tooth, this tooth, and this tooth. Because no matter what position the rotor's at, you always have the exact same amount of overlap here as you do here, as you do here, and so on. So basically every other tooth here is in the same set when you're breaking it up based upon symmetry of the rotor. So yeah, since it's every other tooth, you end up having 2 sets. That's why you have 2 phases. So I'm going to add 2 phases just by clicking this Add Phase button. Now the next step is to define the winding area for each phase. So to define the winding area, or the winding path, excuse me, go ahead and go over here and click a winding area. Now when you click it, it should turn green, and then these drop-down boxes should be enabled. So here we're going to assign this winding area a phase. And right now it really doesn't matter what phase we pick, so I'm just going to pick phase B. And the direction here defines what direction the current is going through this winding. So here we're going into the screen. Now I want this winding to actually wrap around this tooth here. So if it's going into the screen here, I want it to come out of the screen in this winding. So I'm going to assign this phase B again, and I'm going to go out of the screen. Now note that this particular winding just wraps around this single tooth here. For some special windings, it may be the case that you actually want to wrap around multiple teeth. So for instance, I can do this here, and now my winding is wrapping around both of these teeth. So if you visualize this, you think of the wire going into the screen here, going behind both of these teeth, coming out of the screen here, and going in front of both of these teeth. And wraps around both of these teeth 52 times. So that's a case of some sort of specialty winding that you might end up having. But here we're just going to make a very simple winding path that just wraps around every other tooth. Okay. So since this tooth is in the same set as this tooth, this tooth, this tooth, this tooth, and this tooth, we also want to make the windings wrap around these teeth. So I'm going to assign that phase B, phase B. Now we have to be careful about what directions we've assigned these currents. Right? And that's really up to your application of how you actually assign these directions. What the algorithm in the auto set button does is it defines these directions in such a way that the flux tries to take the shortest path it can. So in some applications you might want the flux to go out of this tooth into the rotor all the way across and over here. But here we actually want the flux to go out of this tooth into the rotor and right back into this tooth. Right, a nice short path. That's what this auto set button tries to do. It's not always successful because you may have an odd number of teeth per set, which makes it impossible to always have a nice short path like that. But anyway, in order to force this flux path to go this direction, you have to make the winding direction opposite of this tooth. So this tooth, the winding direction is as follows, and then this tooth, the winding direction goes this way. So now we're going to go ahead and fill in the rest of these winding areas for the rest of the teeth. So now, once we've defined the windings for the rest of phase B, we basically do the same thing for phase A. So basically, all the teeth left we want to wrap around, each tooth that's left we want to wrap around with phase A. So again, we're going to make this so that it follows, so that the flux follows the shortest path. So once you've defined the winding path for both phases, it's time to define when the windings actually fire, or when the phases actually fire. So to do that, we're going to fill in these three columns. So we'll start off with the start angle. So if I take the rotor and just drag it around, first note that this number on the bottom changes as I drag. This number represents the angle of the rotor. And note that this blue rotor lobe doesn't really mean anything special. It's just a marker for a frame of reference for where the actual angle of the rotor is. But note, I don't have to use this reference. I can look at this lobe or this lobe. It doesn't matter. So we'll actually come back to that later. But looking at phase A, I would want the phase A to start firing right about there. Right, so right at about 31 degrees. Or let's just go 30 degrees. I want phase A to start firing at 30 degrees. And I would like it to continue to fire up until right about there, about 58 degrees. So my total angle on is 58 minus 30, which is 28 degrees. So now my phase will start firing here, and it will continue to fire until I reach 58 degrees. Now you notice that it lights up green when the actual phase is firing. So right now the phase is always firing. and that's because we haven't determined, or we haven't set the angle off degree. So the angle on and the angle off represent one step in a cycle. If you take the sum of the angle on and the angle off, that's one step of the cycle, which just continues to repeat. So what you'd actually want for the angle off is most commonly due to the symmetry of the rotor. So, like I said before, I want the phase A to start firing at 30 degrees. So if this is at 30 degrees, right around there, then I want it to stay on until it gets to right about here, right about 58 degrees. Now I want this phase A to turn off until this lobe here gets around to that starting position at 30 degrees. But note that that's not 30 degrees anymore, that's now 90 degrees, right? Because this point here is 60 degrees off from this point, right? This is 360 degrees divided by 6 rotor lobes gives you the angle between here and here. So based upon the symmetry of my rotor, I want this to be 60 minus 28. So that will be 32 degrees. So one thing you want to do is just take the rotor and drag it around here to see when the phases are firing and when they stop. So that was good. That was a good set of firing right there. Now it stops. Now, right about now, I want it to start firing again. I want it to stop. Drag. I want it to start firing now. Stop. Right. So you almost always want the angle on plus the angle off to equal the symmetry of your rotor, right? So will equal basically the 360 divided by the number of rotor lobes. It's almost always the case. So for phase B, you can also fill in these two numbers because these are also going to be the same. Now all we need to change is the actual start angle, which is actually not too far off from what it is. So the start angle, as I drag this rotor around, I want it to start at right about there, 0.5 degrees, say. So I can change this to 0.5 degrees. It doesn't really matter. So now my phases are set. You can see them making a nice switching pattern as I drag the rotor around. So note that this starting angle is not necessarily unique, right? So if I set for phase A, my starting angle is 30, so that's right around here. It's right around here is my start angle. But really, if I move another 60 degrees from there, that's also a valid start angle, right? This is also a valid start angle. So I can change this from 30 to 90, and you get the exact same firing pattern as you did before. Likewise, I can change this 0.5 to 60.5, and I get the same firing pattern as I did before. So that gives you an idea of what this auto set button actually does. So this is all I have for this tutorial. Thanks for watching, thanks for using Quick Machine, and I will see you in a later video.